right, so let's move to the next kind of level of differential equation. It's going to look like this. Dy dx equals f of x, y. So now we're allowing for a function on the right side that involves x's and y, the function y. All right. We can't solve this just by integration because of the the presence of both x's and y terms in the right hand side. And so we have to start thinking about other ways to solve these. Now, the first thing to understand about differential equations is they're notoriously difficult to solve, even first order differential equations, because depending on what that function f looks like, it may be very difficult for us to actually walk away. Remember, when we mean to solve a differential equation, we want to come away with a function y of x, as a solution. So it may be very difficult for us to find a function y that satisfies this differential equation. That being said, we have a couple ways to get around that can still be informative. One way that we won't touch on very much in this class, but actually becomes very useful and actually used quite often in real life, is just a numerical approach. We just give up on trying to find the actual function y itself that solves this, and we actually just find the numerical values of y rather than the algebraic expression for y. And that usually is good enough to answer the questions we're after. A second way is a graphical approach. And it applies to these kinds of differential equations where we have the derivative of y equaling a function of x and y. And so it's a graphical approach. We use what are called slope fields. All right, so let's grab a specific example here. So say dy dx equals x minus y. So there it is. There's our right hand side. And so what we want to do is we would like to come up with, we'd love to solve this ultimately, but if we can't, is there a way we can learn something about the solutions without actually having to solve it? And that's where slope fields come into play. The thing you need to recognize is we may not be able to find y explicitly, but look, we know something about its derivative. We know, in fact, we know the values of the derivative at any given point. Okay, x, y. So here's what I mean is, let me create a real basic graph here. Let's say we're looking at the point, we don't want it to disappear, so let's try that again. All right, so let's say we're looking at the point 1, 1. Okay. We know that at that point, 1, 1, the value of y prime is equal to x minus y, the x coordinate minus the y coordinate. So in this case, it would be 1 minus 1 or 0. So we don't know what the solution y is, but we do know its slope at 1, 1 has to be 0. So we'll put a little line in there to indicate that the curve itself, whatever the solution is, has to flatten out there. So it may look like that. It could look, we don't have much information about the solution curve at this point. But we do know that at that one individual point, it has to, it has to flatten out. And so at that one point, we know something about it. Now, by itself, that one point isn't very helpful. What is preferred is for us to put a bunch of these little slopes together. So let's look at, say, the point 2, 1. So at that point, what does, let's try that again. What does the solution, what's the property that the derivative of the solution has? In other words, what's dy dx at that point? Well, that's the point 2, 1. So 2 minus 1, right, is 1. So at that point, the solution curve has to have a slope of 1, about a 45-degree slope. So we put a little line segment in there to indicate that the solution, whatever it is, needs to, at that point, be tangent to that line, have slope there. And we can continue this, right? We go to 1, 2, and the slope field entry there would be 1 minus 2, right? 1 minus 2. So that looks like that. Now don't panic that, you got these 3 points that are headed in, vastly different directions. The curve that goes through here may never touch this point. So it's okay. We're not trying to find one curve that matches all of these points. You'll see a little bit more clearly here in a second. But if we continue this, let's go to the point 2, 2. Again, 2 minus 2 is 0, so we're flat there. Let's put in just a couple more. And you can do this. I'm doing this graphically by hand. You could make a little table. You'll see a table listed in the text. At the point 3, 1, right, it's going to be 3 minus 1. So the slope will be 2. So I always use, the 45-degree. There's the slope of 1. So 2 is going to be steeper than that, roughly speaking. So there's that. Let's just do one more. This is the point 3, 2. So over 3 up 2. The slope will be 3 minus 2 is 1, right? And so there's just 6 entries in this slope field. Now, to create a slope field by hand is kind of tedious. So we're not going to do that. We're going to use some technology, all right? So probably the easiest to use is Desmos. Desmos actually has the ability to find slope fields, all right? So what you want to do is you want to I've already found this, located this for you. But for you, what you want to do is you just want to go Desmos. You just want to do a little search in there and type in Desmos slope field generator, and it will bring you up to their I don't even know what they call them in Desmos, but a little graphical program that's already been programmed that will let you create slope fields. Okay, now my suggestion to you would be to log in. That way you have the ability to save this and to access it quickly and easily. And the way you after you're logged in, you go over here to these little 3 bars and you go right here, and you're looking at the current graph. If you click save, then that graph will be saved, and it will always show up here and you can access it quickly. All right. So now this is great, and it's pretty much good for our purposes. The only challenges that it has is that it's limited from -10 to 10 on both the x and the y axis, but that's okay. All right. Let's take a quick little look here. This is not the differential equation that we started with. This is a different differential equation. So if we look up here in the text boxes, we can see that the differential equation is sitting right there. It's just reversed. G of xy equals dy dx. And so the question is, what is dy dx? So in this case, the right hand side of our differential equation is 2x over y. The one we were looking at is x minus y, and we'll return to that here in a second. But let's talk about this one for a second. Now let's change it out, because this is how you use this. You change this function to be yours. That's all you change. And then now you have, it creates the slope field at every integer grid line for our graph, and it does. So we just did these, right? We just did these 3 right here. We did that one there. But what you're looking for is this is kind of like a flow field. This is kind of like those things you see on the weather, where they're showing you the way the wind is going to flow. That's what we're looking at. So the solutions to our differential equations are going to flow in this pattern, in these directions, according to these requirements. All right. So you can kind of just see. Let me see. All right. So I've just grabbed this, and hopefully we'll just paste it right in here, so we can draw on it. Let's get it a little more. We don't need it to take up the whole screen. So let's scrunch that down. All right, so there's our slope field for that differential equation, dy dx equals xy. And so, as I was saying, what you're looking for is you just want to understand that. Remember how we have families of solutions. So this is telling us that the solutions to this differential equation are going to have to behave something like that. So that one particular solution might look like that. You know, I'm just kind of, I'm probably missing some things there. But in general, our solutions are going to behave kind of like that. Okay, and you can just kind of see that. Now, remember, this slope field represents all of the solutions. So if we want a particular one, you know, we may want one that goes through a certain point, then there is going to be just one that does that. Now, just for your information, the solution to this particular differential equation is c e to the negative x plus x minus 1. Okay, so if we go back to Desmos, let's graph that. Let's go back to Desmos. And let's just add in here y equal, let's add a list, right? C equals, we'll just throw in a few here. Say, let's go from negative, not those, we want those, negative 3 to 3. All right, and we'll add in here the solution. Y equals c e raised to the negative x, right? What was it? Plus x plus 1, right? Or plus x minus 1. And we should start to see, yeah, there we go. So see how it graphs? This has graphed what, 6, 7 particular solutions for different values of c, and you see how they flow along these paths, right? If we expand this to say, let's go from let's go from minus 10. Let's just see if we have the room here. Minus 10 to 10. Boom. You can start to see that what the solutions do in this case. They have this pattern, they fit this pattern, and this is just by graphing the slope field. All right. Now we may want one particular solution. Say we want one solution that goes through, I don't know, let's have it go through this point right here. Let's go through minus 4, 4. We want the solution that goes through this point right here. Okay, so to do that, we have to go back to our equation and say, okay, we actually are going to add an initial condition, and that initial condition will be we'll just put it in coordinate form, but in a lot of times we'll see it like this, right? Y of negative 4 equals 4. So we need to figure this out. So let's do a little work to figure out what C needs to be. And remember, the process is this. If we plug in negative 4 into the equation, we want to end up getting 4 out of the equation. What C does that for us is the question. So with just a little bit of algebra, we end up getting C equals 9 over e to the 4th. which is approximately equal to 0.1648. So just to kind of verify this, we can actually graph our solution with that as the constant. So this is a particular solution we're looking for, and just verify that it does everything we need it to. So y equals, let's try that here, y equals 0.1648 e raised to the negative x plus x minus 1. And there it is, right? It fits through the pattern, it flows, but also notice it goes through the point. Let's throw this up here. Goes through the point -4, 4, right? I've graphed that. So we've identified one particular solution. So slope fields are really helpful. Now, they don't tell us what the equation is, right? But they tell us qualitative properties of the equation. So we see here that for any solution to this differential equation, no matter where it starts, right? Whether it starts up here or it starts at our point -4, 0, or it starts, wherever it's going to start, it's going to go, and as time progresses, the value of the function is going to become asymptotic to this line y equals x, right? It doesn't matter where we start. If we start down in here, the solution will become asymptotic. So what that's saying is, as time goes to infinity, all of your solutions to this differential equation approach the line y equals x, right? And so that becomes kind of helpful. It tells us some things about the solution. Doesn't matter where we start, this is the equilibrium of the solutions, right? They all get sucked into this line, and that's helpful, and that's found from the slope field. Now let me mention this. We use Desmos. If you want something a little more powerful, maybe to use to find slope fields, you can use GeoGebra. GeoGebra has a built-in, let me resize that. It has a built-in command for doing slope fields, and it is simply just slope field, right? You just type in slope field. Boom, you don't even have to type it all in. Slope field, and in the parentheses you just put in what the right hand side of your differential equation is, x minus y, and you should get a slope field. There it is, right? And you can see the same general flow. So it's a little more powerful because you can do some things with it. I can move this around and it adjusts things as I go. You can see those slopes moving to fit where the origin is. So Desmos offers that as GeoGebra offers that as an option for finding slope fields.